Welcome to first course on power systems, module 11. And in this module, we'll look at control of interconnected power systems and economic dispatch. And here is our reference book here. So in this module, we'll look at the control objectives. And these would be that we control voltage by controlling excitation and some other means of reactive power. And we will look at automatic generation control, so-called AGC. And we'll also look at economic dispatch and a little bit about just a mention of optimum power flow. So first of all, why do we have interconnected systems? Well, having an interconnected system allows us continuity of service because one of the transmission lines may have an outage, one of the generators may fail. So having an interconnected system allows higher reliability in the system. The other reason is that we have economy of operation because then we can use the most optimum generation that we have available. And the third reason is that having a large interconnected system where all the generators participate when there is a change in load, the frequency deviation can be made to be very small. So we'll look at all those in this module here. So here are the control objectives that we have in such an interconnected system. Is first, of course, controlling the voltage, very important. Otherwise, there may be a voltage collapse, and this is done. Well, let's wait. We'll see how it's done. Then we have frequency control and interchange of power between different areas to their scheduled values. And then we talked about this optimal power flow such that power to the load is provided in the most economic manner. Of course, we have to be concerned about the constraints of the transmission line capacities and power system stability. All right, so let's start with voltage control by controlling excitation. And some other reactive power devices. So by and large, the reactive power in a power system is provided by these synchronous generators. And it is controlled by means of controlling their excitation. But in addition, we have other devices available, like these shunt capacitors, shunt reactors, the static war control unit, which using thyristors can switch in or out capacitors. Then we have STATCOM, which is a power electronics-based device, where you can supply injected current leading by 90 degrees or lagging by 90 degrees. And then we have some other means like series capacitors, including thyristor-controlled series capacitors. And also if you have high voltage DC, especially the types which use voltage link systems, then we can control reactive power in a power system. All right, so let's begin with the excitation control of synchronous generators. And as I mentioned earlier, these synchronous generators are the primary means by which we supply reactive power, which then ends up controlling voltages at various buses. So, we have seen how these synchronous generators operate, and in the rotor of these synchronous generators is a DC field, a DC current, and by controlling this DC current, we can make them overexcited, in which case these synchronous generators provide reactive power to the grid, or we can make it underexcited, in which case they draw reactive power. So one of the ways to supply to control this DC current, and therefore the excitation of these synchronous generators is shown here, where you measure the voltage at some bus, where you want to regulate it to a certain value. You compare it with his reference, and the error between the two then controls this thyristor control rectifier over here, and thereby an appropriate amount of DC current flows in the rotor of the synchronous machine, and this DC current is provided. Rotor, of course, is rotating, so there are slip rings on the rotor, and then through brushes, this current is supplied to the rotor of this machine. So here we have slip rings and brushes, but there are other ways to do it is by means of so-called brushless exciters. We'll not go into the discussion of those. And then some large generators are equipped with so-called power system stabilizers. And the role of these power system stabilizers is to provide damping in the system. So they see the rotor oscillations of these generators and use that as a signal to control the excitation such that additional damping is provided in the system. So this is quite commonly used, especially with large generators. So moving on to the next topic, and that is on automatic generation control, AGC. Here we want to make sure that the generation meets the load demand, both in steady state and on a dynamic basis. Okay, so we want to design it such that both of these objectives are satisfied nicely. So what has happened is that the whole interconnected North American system, as you see here, has been split into different control areas, and each control area may consist of many utilities there. And just an example, so on the left, you see how these control areas are now, I think they're called balancing authorities. They are shown here on the left, and just an example of these control areas interconnected by transmission lines. Quite often they're called tie lines, is shown over here in figure B over here. So we'll see how what the role of these control areas is. But before we look at that, let's just look at one generator, okay, and how it, what is the load frequency control and regulation in this generator. So as you can see here, we have a turbine where steam is coming in, and it is producing this power P sub m. And in steady state, if you ignore all losses here for discussion purposes, the output PE is equal to P sub m over here. Okay, and if so, what is done is that by design, a drooping characteristic is given to this frequency load characteristic here. So frequency is plotted on the vertical axis, and the load is whether it's mechanical or electrical, doesn't matter, they're the same, ignoring the losses in steady state, is plotted on the horizontal axis. And the characteristic is given by this G prime straight line, and as you can see, it's drooping, and the slope of this is minus times the regulation R, which is defined here. So this regulation is really this minus sign times the change in frequency to a change in load. So as you can see from this diagram over here, that if the load were to increase, and therefore the power that is coming from the turbine is to increase by this amount over here, it will result in the frequency drop by this amount delta F. So the operating point would shift from A to B. So this delta F is a negative value, and therefore by having this minus sign here, this R really is a positive value here. And you can also see in this diagram on the left here that if the load were to increase, you can see that the frequency here would drop, and so that's a negative value, and then divide by 1 over R, or divide by R, I should say, but with a minus sign over here, what it will do, this is a negative value. If the load were to increase, then you have a negative sign over here. So this eventually ends up changing the valve position in a way that more steam is coming into this turbine over here in order to increase the load or the power output of this turbine to meet this increased load here. So that's what this regulation is about, and by design, this characteristic is made to be drooping, as shown here. So now let's see what happens if we have two, just as an example, two units, okay, and they are connected by a tie line, a transmission line, and again, we'll ignore all losses for our discussion purposes. And so unit 1 has this characteristic G1 prime over here, this prime, actually just G1 here, sorry, given by G1, and unit 2 has this characteristic here between these two here. So in steady state, the operating point for unit 1 is A, and operating point for unit 2 is B over here. Okay. So now if there is a change in load, then what's going to happen, and this change in load is occurring only on unit 1. Okay. So if there is a change in load on unit 1, you can see that this change in load causes the frequency to drop. Okay, and this frequency will drop for both units, right? So, and how much does it drop? Well, pictorially we can see that if this frequency were to drop to this value over here, then the operating point would shift to C for unit 1, and it will produce this extra power because more steam coming in. And for unit 2, this drop in frequency, same drop in frequency, will shift the operating point to D, and that will cause this much extra power to come in, and the sum of these two is equal to this change in load, right? So knowing how much is the change in load here and what the characteristics of these two units are, we can determine what this change in frequency would be. And mathematically we can express it with this equation over here, and you can see that if we had only one unit and this second term was not there, then the frequency excursion would be larger. But having the second unit, in addition to this term, we have this term as well, so this frequency excursion is smaller, right? So at this point, we haven't really talked about changing the characteristic for any of these units. So this straight line that you see given by G1 and G1 prime, we haven't talked about that. We will talk about it in the next slide. So mathematically or graphically, you can see what happens when you have this interconnected system using two units with a tie line to a load chain, let's say on unit 1. All right. But let's say that we have that unit 1 is equipped with so-called automatic generation control. And so the role is that if the change occurs on unit 1, perhaps unit 1 should absorb all that load, and unit 2 should be unaffected. And because that you may want to do because there is some purchase agreement between units 1 and 2, and the tie line flow should remain unaffected. Okay, so unit 2 output, the flow on the tie line should remain the same. So what we'll do is, for the same change in load that we talked about, where without changing the characteristics, the change in power output of these two units was PM1, delta PM1 and delta PM2, what we'll do is we'll raise the characteristic of unit 1 to this straight line over here, okay, such that the intersection point for unit 1, the operating point is E, and you can see here that now with respect to the initial operating point of A, the change in output is equal to the load change, which is the sum of this and this over here, and therefore there is no change in frequency, and unit 2 keeps on operating at point B over here. Okay, and that way the flow on this tie line would not be affected, even though there is a change on load in load on unit 1 on unit 1. Okay. So that was okay in steady state. How does it work under dynamic conditions? So to look at that, we will define something called area control error, ACE, ACE. And this control error, let's say we have two areas, and they're connected by a transmission line of this reactance here. And we will define the area control error for area 1 as the change in power flow from area 1 to area 2, which is this much, plus a frequency bias factor, just a coefficient, times the change in frequency that occurs here. Okay. So the objective here is that by proper control, we should have in steady state no change in frequency and no change in inter-area power exchange. Okay, even though the changes occurred either in area 1 or area 2. In a similar manner, we will define the area control error for area 2, where the change is in this power, P21, defined in this direction, and they are equal and opposite if there is no losses, but certainly those could be accounted for. And in addition, you have this term due to the frequency change, where B2 is the frequency bias factor for area 2. So we define these two. We define this area control error in this manner, and the way it operates on the steam valve position is shown here. So we had seen earlier that frequency deviation based on this regulation here acts on this governor with this negative sign and changes the valve position. But in addition, we have a supplementary control signal that depends upon this deviation in tie line power flow and this change in frequency through this frequency bias factor. The sum of these two gives us the area control error, and that acts on the supplementary controller, and again with a negative sign. These two add up and act on the governor to change the steam valve position. Okay. So in steady state, we'll see an example here, going back to our 3-bus system that we have been talking about. Let's say that this is the picture here, where area 1 is to the left of this dotted line, and it consists of this unit here, and then area 2 is to the right, so it consists of this this unit and this load over here. Okay, and the power is being metered at the end of this line as shown here, and at the end of this line 1-3 over here as shown. All right, so here we'll see what happens if there is a change in load. How would these two units behave? So that's what we are going to see in the next slide. So for a given operating condition, initially, we have this figure A, and all losses here have been ignored. Okay, so the load is 5 per unit. Okay, on some MVA basis, usually taken to be 100, I think. And you can see that generator 1, this generator is producing 3 per unit. This generator is producing 2 per unit here. And you can also see the flows on these 3 different lines here. So now there is a change in load. This 5 per unit becomes 6 per unit. Okay, so there's a 1 per unit increase in load, and see what happens in steady state. Initially, this unit at bus 1 was producing 3 per unit. That keeps on producing 3 per unit. But this unit 2 now is producing 3 to meet all the change in load in its own area, because this load and this unit, they're in the same area over here, right? So this unit connected over here ends up meeting all the increase in its own area, and you can see what happens to different line flows, and they all match up. Okay, so you can see that sum of this and this is equal to 3. Similarly, sum of this and this is equal to 3. And the same thing you can say about, you can match up with other lines and generation. So that's what ends up happening.